assignment which is related to the gravitational field or the gravity. In question 4, the Hubble Space Telescope, which is HST, was placed in an orbit in 1990 with an aim to produce a high resolution image of astronomical objects. HST, the Hubble Space Telescope, is in a low Earth orbit at a height of about 269 kilometers above the Earth's surface. The orbit is nearly circular and its plane is inclined at an angle of 28.5 to the equatorial plane. The radius of the Earth is 6.3 into 10 to the power 3. Show that the strength of a gravitational field at the height of the Hubble Space Telescope is about 8 Newton per kilogram. So we have to show that the value of the gravity about this one. So the formula which relate the gravitation field strength. So what we can do, like say this is the Earth. So this one is representing the space telescope HST. And it is 569 kilometers above. So like this distance is 569. And the radius of the Earth is 6.3 exponent 3 kilometer. So the total distance will be equal to the sum of these two. Now, what we can do in the question, they did not provide us the mass of the space telescope, even they did not provide us the mass of Earth. So what we can do, we can use this formula like the value of the gravity is equals to G, the mass of Earth over R square. Like the value of the gravity is equals to G, the mass of Earth, and the distance between the object and the center of Earth, that is, or planet, that is R square. This is a formula which relate the value of the gravity. So what we will do first, we'll write an expression for gravity on the surface, and then we'll write an expression for a gravity on the space telescope, and then we compare the two equations. So if I want to write the first one, so this will be G1, the gravity on the Earth surface. I say G1 is equals to capital G, the mass of Earth, and radius like R1 square. Or I can say G1 R1 square is equals to G into mass of Earth. And the second expression, what I can do, I can write for the space telescope, the Hubble Space Telescope. That is gravity at that Hubble Space Telescope example, I say G2 is equals to G, the mass of Earth, and R2 square. And what is R2? Like R1 is actually the radius of the Earth, which is 6.36 into 10 to the power 3 kilometer, but we should always use in meter. So it will be 6.3 into 10 to the power 3. I'm writing in kilometer, but we'll convert into meters. And R2 will be the sum of the radius of Earth plus the distance between the telescope 569 telescope and the Earth center. So R2 is the sum, R1 is the radius. So if we can write, we can say G2 into radius, the second radius, orbital radius is equals to G and ME. We have two equations, so we can compare like GME and GME are same. So we can compare them. When we compare, so we can say that G1 radius of Earth 1 square is equals to G2, the second value for gravity is R2 square. So we just have to substitute those values and find the new value for gravity on the space telescope. So the first value of the gravity was 9.81. the radius R1, that is 6.36 into 10 power. It is 3, then we convert kilometer into meter, we multiply by 1000. So it will become 10 power 6 equals to the second gravity we don't know. And this one will be equals to 6.36 into 10 power 6 plus 569 into 10 power 3. This whole is multiplied, other side will be divided. So we'll get the gravity, the value of the gravity on the surface on this space telescope, which is about 8.26 Newton per kilogram. Is it clear, this part? In the second part, by considering the gravitational force acting on the Hubble Space Telescope, calculate the time for Hubble Space Telescope to make one complete orbit on Earth. So how much time it will take to completely move around the Earth? So the value of the gravity is 8.2, which it is 8.26 Newton per kilogram. Now what happened? Like the gravitational field, gravitational force is acting. So we can say as it is moving around, like moving in a circular path, so we can say the gravitational force is equals to centripetal force. So the centripetal force and gravitational force are same. Centripetal force is given by m r omega square or mv square over r. And gravitational force is g, the mass of the Earth, mass of the satellite or like the object, and r square, that r is actually a distance between their center, so which is equal to the sum of radius of the Earth plus the orbital like height above the Earth. So this is the Earth. So this r, the total r is equal to radius of Earth plus how high it is above. So it will be r will be equal to radius of Earth plus h. But we simplify, cancel out, r cancel out with r, and sorry, not r, m cancel, because it will be multiplied there. M will cancel out with m, and r will be multiplied there, so it will become r cube. So this will be equal to r cube omega square is equals to g, the mass of Earth. Then first we'll work out, because we have r, we have g, and mass of Earth is a constant, which is there at the end of the exam paper. You will find the value of constant. So first we'll work out omega, and after working out omega, omega is equals to 2 pi f or 2 pi divided by t. So t is equals to 2 pi divided by omega. So first we work out the omega. So omega is equals to g, the mass of Earth, radius r cube, and then take a root. Why? Because that is omega square is equals to g mu over r cube. So omega is equals to under root g mu over r cube. This will give us the value for angular frequency. This is one way of working out this. There is also another way, because in this case, the gravitational force is g mu over r, or the gravitational force is also equal to weight. So I can solve in this manner, like using the mass of Earth, radius, and g, and take a root. This is one way. What is the second way? The same formula we can use. And the gravitational force in this case, because the force by which the Earth is pulling the object towards the center equal to weight of an object. So this gravitational force is equal to weight of an object. So it can also be mg. Then m will cancel with m. Like this, m cancel with m. So we can say omega r omega square is equals to g, or omega is equals to g divided by r in inner root. So value of the g, it is 8.26. Value of the r, which is equals to radius of Earth plus the height above the Earth's surface. So radius of Earth was 6.3 into 10 power 6, because we convert into meter. And this was 5.69 into 10 to the power 3. Taking a root, this will give us a value for omega 1.09 into 10 to the power minus 3 radian per second. After having omega and 2 pi, so we work out the t. So it will be 2 into 3.14 divided by omega 1.09 into 10 to the power minus 3. This will give us the time it will take to orbit, which is about 5,755 seconds. This is the total time it will take to orbit the Earth. Is it clear? Which is about like 1.6 hours. So both ways you can get the time period. First find omega and from omega work out the time period. Communication satellite stays above the same place on Earth at all time. State and explain two changes to orbit the Hubble Space Telescope for remain above same place surface at all the time. Like in this case, like the Hubble Space Telescope, we want its time period, like we work out it's 5,755. So if you convert 5,755 second into minutes, you divide by 60, it's about 95 minutes, and you convert into hour. So it's taking about the time period, it's taking about 1.6 hours. So first thing, if we want to keep its speed same, we should increase the orbital distance. Like here it is at a height of 569 kilometer. So if we want to make it a geostationary means it does not change its position with reference to the Earth. So we want to increase its orbital time period to 24 hours. And to increase this orbital time period to 24 hours, we have to increase the distance or height above the Earth's surface. Like it should be far from the Earth's surface, so the orbital time will increase. So it will become a geostationary, like it won't change its position with reference to the point on Earth.